thanks to the organizers. Great to know this. Very nice to meet. I met Sergey, I think, in 1998 semester, mostly with smoke breaks and lectures. But I think friendship survived your abandonment. And Kobe, I think maybe that semester or soon thereafter, in any cases, a long friendship. And I'm very happy to have this chance to congratulate them. For this. Before I start, if I can make a little advertisement. A year ago, we started this new journal called Bone Theory, published by MSB at Berkeley. And we now have our first issue published. It's available online for free. In fact, the journal will remain free for at least another year. And so I just encourage people to check it out and to consider submitting to it. So I'm going to be talking about some joint work with Remi Jaoui. A paper that was posted to the archive just last week. So the setting here is model theory of differential fields. So let's take T to be differentially DCL0, differentiate both fields, characteristic 0. What I will talk about is true also in several commuting derivations for finite dimensional types, and also in the theory of compact complex manifolds. But for familiarity, I'll stick maybe to DCL0. It is really a geometric, something in geometric solidity theory, and at least the part that I will talk about today works in some more general setting. And I'll try to recall the various notions of geometric solidity theory that I use as I go along. But if I say something that needs clarification, please ask definitions. But we fix this theory and we work in a sufficiently saturated model U. And let's denote by C the field of constants. So this is a pure algebraic closed field defined in the theory. And I'm going to be talking about orthogonality, which has showed up twice already in this workshop. Dave talked about it, but I think in the context of strong and minimal defining sets, and Alessandro talked about it in a very general setting. The focus here will be a little bit different. It will really be about parameters, which somehow didn't come up in those discussions. So, and I'm going to talk about types of orthogonality for a type. So let me just recall some definitions. So suppose I have a type over some parameters, and I'm going to always assume that my types are stationary, meaning that there's a unique non-formal extension to any larger parameter set. And you can always achieve this by taking B to be algebraically closed, so we could assume that if you like throughout. And so ACL closed, which is on Dave's talk, means that it's an algebraically closed differential subfield. So P is said to be P is weakly C orthogonal. So I'm only going to be talking about orthogonality with respect to the constants here. It's weakly C orthogonal. I'll denote this by weakly C orthogonal. If, well, there's no relationship between the type and the constants, but the weakly here refers to over these parameters, so without any additional parameters. So if you take any realization of P, then it is independent from the constants over the parameter set. It doesn't fork with any constants over the parameters that we're working with. Okay. To be fully orthogonal, so P is orthogonal, if this remains true after you extend the parameters. If for all, say B prime containing B, and let's denote by P sub B prime the non-formal extension. extension of P to B prime, then P prime is weakly orthogonal. So here now I'm allowing not just, and I'm saying not only are they independent over B, realizations of P independent over B, but realizations of P are independent over any extension of parameters. I mean, if you take a free extension of P to B prime, then it remains weakly orthogonal. So the difference here is really a sensitivity to what parameters you allow to witness the relation. So maybe the example to keep in mind, very basic example to keep in mind, is just the equation delta x equals 1. So this is weakly orthogonal to the constants because, well, if you take a realization here, if it forked with some constants, I mean, this is a strongly minimal set, so it would have to be algebraic for the constants, but the constants are algebraically closed, so it would have to be a constant. It's not a constant. It's very useful. On the other hand, it's not orthogonal with constants. In fact, it's just a coset of constants. Once I give myself a parameter, one realization, let t be a solution, so the derivative of t is 1, then I get all the other solutions. In the equation, I get all the other solutions by translating by that solution. So the set of solutions is definable by ejection of the constants. It's just a copy of the constants. But only if I have, it's a coset, so I need one solution to witness that. So once I go to initial parameters, I have a lot of interactions. But if I don't have any parameters, I have no interactions. This is the kind of situation that we're interested in. Okay, the fact here that the solution I needed was, the parameter I needed was a solution to the equation is not an accident of this equation, it's generally the case. The general fact of geometric stability theory is that if P is not orthogonal to the constants, after you extend parameters you have interaction with the constants, then those additional, to witness that, the additional parameters you need to take themselves may only be realizations of P. So then P to the n is not weakly orthogonal to the constants for some n. Right, so in this case, I needed one parameter, one solution, t, to witness that there's some interaction with constants, which means if I took two solutions, then the second solution would fork with the constants over the first solution. So in this case, P2 would not be weakly orthogonal. P1, P itself is weakly orthogonal. P2 is, I should say, so Pn here is the Morley, we have the Morley power. So Pn, so here, Pn is the type of an independent n-tuple of realizations. It's a stationary type. So for every n, there's a unique n-type for an independent sequence. Now all n independent sequences have the same type, and that type is denoted by P with brackets.
Is it even on the
Yes, it's also exactly. So this being not weakly orthogonal means that you have an n-tuple which is going to fork with something. So the first n minus one of them are the parameters you need to get forked with the constants. So we apply sort of strong, looks like a strong version, but it is equivalent to non-orthogonal. So the theorem I want to talk about, which is part of this paper, with it's one part of the paper with Remi. Maybe I'll call it theorem 1. Is that if we work over constant parameters, this is going to be about the case where the parameters are themselves living in the constant field. So this is the so-called autonomous case. We have a stationary type. Then, if P is not orthogonal to the constants, if P is not orthogonal constants, then already its square is not weakly orthogonal. General need n, and the theorem is that in DCF0, this is very general in a stable setting. But in BCF0, in the autonomous case, you only need 2 realizations. You just need to take the second power. It's not clear. It's not an n. It's a 2. I'm not sure how that looks anymore. So maybe a couple of remarks. First of all, you really need autonomous here. So if you look even in BCF0, but you allow arbitrary parameters, not necessarily constant parameters, then there can be no bound on how far you have to go that's absolute. It would have to depend at least on the dimension of the type. By the way, by the dimension of the type, I just mean the transcendence degree. You take a realization and you look at the differential field it generates. So you look at all the derivatives, and the field that generates. That's a field extension of the base. Transcendence degree is what I mean by dimension. And in general, you know, there you could construct examples where you need at least that.
Transcendence degree over the set of parameters over which the type is considered.
Yes, yeah. So everything here is over the parameters. So in general, you have to, you have to take at least n plus 2, where n is the dimension of the type. But in the autonomous case, it's absolute number 2, which is precisely what happened in this example. The point is that more or less what always happens. You just need one parameter to do this. So that's one remark. The other remark is that this can be phrased, you can write down a geometric version of this. So this is really, it can be stated, presented in the paper as an application to the birational algebraic geometry of vector fields, algebraic vector fields. Everything here has a geometric translation, right? So a type, finite dimensional type, is the generic type of an algebraic vector field. So an algebraic variety equipped with sections of tangent order. So the classical notion associating each point on the variety in some tangent direction. So that's really what you're talking about when you're studying finite dimensional types. And it being not weakly orthogonal, type not being weakly orthogonal to constants, geometrically that means that there are no first integrals, no rational first integrals. So a notion that has some geometric content. And so this would be phrased as saying that, okay, but actual orthogonality is a bit harder to state the definition geometrically because you have to take these base extensions. And now you're no longer with a constant, so it's not really vector fields with d varieties. And so it can be phrased, but it would look more complicated. But if we use this characterization, then everything can be stated in terms of weak orthogonality. So this statement is saying that if you have an algebraic vector field such that when you take the Cartesian square of that vector field, if there are no integrals, no rational first integrals, then that's true for all Cartesian powers. So this has a geometric statement. But I'll work purely geometric stability there. Right, so I want to say some things, about the ingredients of this proof. Let me right away point out that really, while the assumptions are non-orthogonal to C, you quickly reduce to something much stronger. So you can reduce to C internal. So let me recall that type P is C internal. So again, stationary type over parameters P, not necessarily constants, in general, it's the definition of internality. If there exists some extension of the parameters such that the type is definable. You look at the set of realizations of the type. Any realization of the type is a definable closure of these additional parameters together with some constants. So it's a strong form of being not orthogonal. If you're not orthogonal, then over some extension you fork. And here the forking is witnessed by a definable function. So it means to not be C internal. But the theorem almost immediately reduces to that case because of the general fact in geometric stability theory that when you're not orthogonal, that's going to be witnessed by something that's internal. So, in fact, so if P is non-orthogonal constants, then there is, let me say it this way, a definable function P to Q such that Q is C internal. Maybe I should say what I mean by definable function. I'm not sure it's totally standard terminology on types. I just mean, so P to Q definable function. I mean entirely over the base parameters. So means, first of all, that Q is also over P, and there is a B definable function. F, such that if you take any realization of P, then F evaluated at A is a realization of Q. There's a definable function from the type P to all definable B. And this is a general fact that when you have some relationship with the constants, then in fact, over the parameters B already, there is some image which is a very strong relationship with constants. But of course, internality itself is very sensitive. Right. Yeah. Sorry?
There should be a condition on the function, right?
A condition on the function? You mean of the being definable? Oh, you mean the statement, right, right. Also, yeah, sorry. Q should be non-algebraic. Q is the internal. Right, thank you. And non-algebraic. Right. Is that what I mean? No, I mean if it's yeah, it should not be, yeah, right, sure. Not the actual. You have some real interaction with constants, and there's an actual proper image, non-algebraic, positive dimensional image, which is internal. So, good. So there's two ingredients of the proof, and I'll say a little bit about both. One of them works in a kind of general setting. It's just using geometric stability theory. I'll write the setting down in a second, but it's not specifically really about differential fields. So those are the prime examples along with CCM say. But it also does not require this autonomous assumption of the constants, of the parameters being the constants. The second ingredient will really focus on DCF0 and the constants. So let me talk about the first ingredient. This is questions. So this first ingredient is Abelian reductions. So what's the setting here? So now I'm going to be a bit more general, but you can keep DCF0 in mind if you like. So T here is just any complete omega stable. Well, maybe I say totally transcendental theory, because the language might not be palatable, for example, CCM. Let's assume it admits elimination of imaginaries, but you could just work in EQ. And there has to be some zero definable, pure algebraic closure. That's my only assumptions for this first part. So there is some fixed algebraically closed field, I guess of characteristic zero. Some fixed algebraically closed field, which is definable in your structure, it's like zero definable, and it's pure. So there's no further induced structure on that. So this is true of this C in DCF0, the constants are pure, zero definable, pure algebraically closed field. And this part of the argument will work in this general setting. And the main point here is in the approach to this problem is to use binding groups. Right? It's not a theorem about definable groups, but it uses the structure of definable groups to prove this about general types. So I now have a type P in S of P, stationary, and C internal. So yeah, maybe I should have said because of this fact, the theorem is really saying that if P is C internal, Yeah, maybe I should just spell this out. I mean, so now Q is, maybe I should say that, right? So if P is non-orthogonal, which is our assumption, then it has some image Q, which is C internal. And now if I know that Q squared is not weakly orthogonal, then P squared will also not be weakly orthogonal, because Q squared is the image of P squared. So it has, if you have the realization of Q squared, which forks over the base parameters with the constants, then just take any pre-image of that, and that will fork constants over the base parameters. So really, to prove this theorem, we just need to prove that when you're C internal, so it's sort of strong form of orthogonality, then P squared should be weakly orthogonal. So that's what I'm aiming at in the sketch. C internality implies P squared is weakly orthogonal. So we study internal types, and that's what I'm doing. And the main tool we have to study internal types is the binding group. Maybe I should set this. Next. So we have the binding group P. Maybe I should change this. Right, I don't want to mix it up with, I'll put it here. Which let me denote by aught of P over C. So just my notation is the binding group. So what is it abstractly? Well, it's permutations of P, as the notation suggests. It's elementary permutations of P, which fix the constant. I'm going to refer to this C as the constant, even though the general setting is fixed definable set as the constant. So which fixes the constant, point constant. So you can view it as the restriction to the realizations of P of automorphisms of your structure, which, well, first of all, should fix the base parameters. It's identity on the parameters B. B is always the parameters for my type. But also, when you restrict to the field constants, you'll get the identity. So this is describing it as an abstract group. It's a quotient of the automorphism group structure. But the binding group theorem tells us that it's actually definable, B definable. So binding group theorem tells us that this group is B definable. So this is maybe
So you not assume that G is contained in the constant.
I don't, yeah. So there's no
Because in the
such.
theory you assume that.
I did in the theorem, right? So I should say it's not necessary. It's not necessary. That'll come up in the second ingredient. First ingredient is completely done. That this is B definable. And moreover, the action, this has a natural action on P, right? Permutations of P, and its action on some realizations of P is also B definable. I mean, relatively definable. I mean, I'm in a totally transcendental theory, so that type definable groups are definable, but this is a type definable set. So I mean, the definable group acts relatively B definable on type definable set. But the case we're going to be interested in, P is not going to just be internal, it's going to be weakly orthogonal. Right? I'm trying to show ultimately that P squared is weakly orthogonal, so it's not weakly orthogonal. If P was already not weakly orthogonal, there's already forking between P and the constants, then certainly that's true of tuples. So I might as well assume that P is weakly orthogonal. So if P is weakly orthogonal to the constants, then this group, this binding group, acts transitive. On some solutions, right? I mean, if you have two solutions of the type, two realizations of the type, they're both independent of the constants because of weak orthogonality, and so by stationarity, they have the same type over the constants. So there's an element of the binding group taking one P. So acts transitively on P of U, and consequently, if you like, P is isomorphic. Actually, that's the type. I mean, I would define the group acting transitively on it. So the orbit is defined. The type definable set is actually defined. So in the case we're interested in, we actually get. So what do we get? So we get that I have a definable. So this ought P over C together with the realizations of this type is a B-definable homogeneous space. Transitive action of define the group of define the set, everything is defined with B. And I want to exploit this action. Okay, but we know something more, where everything is internal to the constants. So this group, this definable homogeneous space, the group in its action, is in fact defining the isomorphic to something living in the constants, inside. So, but possibly using additional parameters. So let me say it this way. So we also know, maybe I'll just call it G, binding group of P over C, is definably isomorphic, not necessarily over B. So possibly over more parameters. With, let's write it as H of C, where H is an algebraic group, where H is connected algebraic over this field. So I have this pure algebraic closed field structure on the complex on C, and so I have algebraic geometry living in my structure. Right? This assumption that I have this pure zero definable algebraic closed field means I have, all the algebraic geometry in my structure, and this is saying that this group is in fact the C points of some algebra. Defining pure field. But in general, you need parameters to witness this. It's not a canonical copy, but there is a copy. And the idea now is, well, this is an algebraic group, so we have a Chevalley decomposition of the group. It has a canonical decomposition. It's an extension of the Abelian variety by linear algebra. And I can transfer that back to G. So we get a definable Chevalley decomposition G from my binding group, namely as an extension short like sequence like this, where, well, L is the unique maximal definable subgroup that is definably isomorphic. Again, possibly with parameters, to a linear algebraic group in C, in the field. And A, we call this the linear part. The linear part of G. So, I mean, in principle, it looks like I needed parameters to compare G and H. So maybe I need parameters here, but because of the canonical nature of the subgroup, it's actually B-definable. So this is L is B-definable. So this whole exact sequence is B-definable. And now it's normal and connected, and the quotient is going to be definably isomorphic. A is definably isomorphic to a Abelian variety. C, and I call this the Abelian part. And it's also B-definable. So at the level of the binding group, I have this decomposition of the group. The theorem is that that decomposition is reflected in the type itself. So I'm going to write it here. So I'll call this theorem 2. So I have type, so stationary type over B. Let me take B to be algebraic closed. Don't have to worry about stationarity. And it's the internal. I have C internal type in this setting. Then there exists a definable function from P to another type, which I will refer. So this is also run out of this quickly.
Oh, you got it. Thank you.
So there's a definable function from P to another type, which we'll call P ab, or Abelian reduction, such that the following properties hold. So first of all, let's give it a name for the definable function, F. So F is actually a fibration, by which I just mean that the fibers of this function are stationary. So if you take a realization of P, then the type of that realization over B together with F of A is stationary. That's what this is. We call this. This is a final function between types. This would be the fiber of that. Yes. Yeah. So right. So I think I wrote it up there somewhere.
The statement is definable functional.
Yes, so the definable function, when I say definable function between types, I mean types come with some domain. So P is over B, P ab is over B, and the definable function. So, yeah, so I think I wrote that somewhere up there. Yeah, so definable functions are always on types, they always be not over summation. 2, well, the binding group of P ab. So P was C internal, so this image will also be C internal. It has a binding group, and this is an abelian variety. In C, I'm doing shorthand. I mean defining the isomorphic with possibly additional parameters to the C points of the abelian variety. Okay? I'll just say is an abelian variety in C to mean that this definable group, after adding additional parameters, is defined to be isomorphic, just like here, to some algebraic group. But the algebraic group is and it has the universal property with respect to this property. So if G from P to Q is any definable function, again, by definable function here, I mean all over B, with the binding group of G, an abelian variety in C, then G must factor through F. It factors through this abelian reduction. i.e., so I have P to Q that I'm being given. The theorem is asserting the existence of this fibration, and the universal property says that this is the largest abelian. This is the largest image whose binding group is defined against and part 3 is that if I assume, in addition, that P is weakly orthogonal to the constants, which towards theorem 1 will be an assumption of allowed. It's not just internal, but itself doesn't fork. You have to go further before you see forking.
So in this universal property, you do not assume that G is a fibration.
I don't know. So the universal thing turns out to be fibration. If P is weakly orthogonal, then this this binding group of the P ab is the abelian part. of the binding group. This is what I mean by the, sorry?
Possible that stable type of the algebraic type.
Yes, it is possible. So it might be, for example, with that. Yes, yeah. So I'm allowed to do. In fact, to be honest, I should be, yeah. So I should be more careful. This works. I really should. This is really about possibly non-connected immunity products to start with. So I just mean projected algebraic group, really. So finite, you know, in the same. Though the binding group this guy will be connected, so it will be a group, right? But in terms, for example, the universal property, I just require that it could be trivial, but it could also be finite and all that. But yes, it could be trivial. For example, if the type I started with, if the binding group was linear algebra, which in some senses, in differential Gauss theory, you're usually working with linear algebraic binding groups, then it has no Abelian part, right? Then this is trivial, and so yeah, will have trivial binding group, it will actually be realized. Okay, and so this is what I mean by reflecting the Chevalley decomposition. At the level of groups, we have this decomposition, and this is saying at the type level we can witness. And this theorem 1 is an application of this that I'll describe. I won't say much about the proof. In fact, yeah. So there isn't. I mean, you can imagine, right? It's a pretty general setting. There isn't too much. It's really geometric stability theory. The first part, getting this going, we call this Abelian reduction.
Sorry, but in this theorem too, there is nothing about this linear part L, yes.
Right, but I mean, there's nothing about explicitly stated about the linear part, but somehow the fiber will have to capture it.
Logical fiber is the L, right?
Sorry?
The logical fiber is the L.
Well, no, yeah. I mean, yes. The problem is the fiber is not over B, right? It's over some additional parameter. It's 5. Yes, that will capture them. So F from P to Pf is called the Abelian reduction. I mean, by the universal property is unique up to interdefinability, so we call it the Abelian reduction. So finding the Abelian reduction, you do what you imagine. You look at images who have binding groups of Abelian variety, and many of them, maybe you try to put them together and find an maximal. Basically, do what you expect. You have to use some properties of Abelian varieties, but also some geometric stability theory, economical basis, and so on, to actually prove it, to show its vibration, that it exists. It's a maximal in interest variety. Part 3, when you know weakly orthogonal, you use some Galois correspondence. So the binding group theorem gives you a group action, but you also have if you're fundamental, then you have a Galois correspondence. Over a fundamental system, you have Galois correspondence, and so you have to pass the fundamental system and use some further argumentation using the Galois correspondence to prove that you actually capture the full Abelian. Right. Should we just spread it out? Yeah. So immediate corollary of this Oops. So the same setting, P in S and P, C internal, and weakly orthogonal constants. Then if you know for some reason that P has no proper vibrations, well, then you should know something, right? Because there are no proper vibrations. So the conclusion is if there are no proper vibrations, then binding group must be equal to either its linear part or its abelian part. So in this extension of the binding group, either the abelian part trivializes or the linear part trivializes. And they have one or the other. So maybe I should say, I mean, this is, I think.
So what's proper?
Yeah, so that's what I'll say. So proper vibration, well, maybe I just prove this and then the definition becomes clear. So I look at this vibration given to me by the theorem. So the fact that there are no proper vibrations means that P ab is either algebraic, it's stationary, so realized, P ab is realized in B, or P equals P ab, by which I mean it's a one-to-one definable function. It's usually finite. So a proper vibration is a vibration of a definable function where the image is not algebraic and the fiber is not algebraic. So it's really an intermediate. So if I know that for some reason there's no proper vibration, then the abelian reduction has to be either itself or nothing. And the former, if it's a realized type, implies that the abelian part of P is trivial, right? Because the abelian part of P is the binding group of P ab. If P ab is realized, its binding group is trivial. So I get that the abelian part of P is trivial, but by this Chevalley decomposition, if the abelian part is trivial, then G agrees with its linear part. And similarly, the latter, if P is equal to its abelian reduction, then the abelian part of P is odd. So that just says that it's equal to its abelian part. So very abelian right. So I wanted to this is the first ingredient we'll use to this problem. The second ingredient is a fact from, so this is the second ingredient is a fact from differential Galois theory. So now I really have to work in DCF0 and in the autonomous setting with constants with parameters are in constants, then there is a failure of the inverse differential Galois problem. Dramatic failure of the inverse differential Galois problem, namely the following fact, it's true. If there's enough if ought of P over C is linear, then it has to be commutative. Right? So no non-commutative linear algebraic group can arise as the binding group of a type over the constant. Specific field. And that's all I need is my second ingredient. And now I can prove theorem one. You just put these things together. So remember what I'm trying to prove. I'm trying to prove that if P is C internal, then P squared is not weakly orthogonal to constants. And here B is in the constants. Well, after that second, T is DCF0 and B is the constants. So how do we do this? Well, first of all, there exists some definable function over B, such that Q has no proper vibrations. Because you just, if you have a proper vibration, you take it, and it's proper, so it's a smaller dimension. Right? The fibers are not algebraic. And then if that has property, you do that, and eventually it's just stop, and you get a type. It doesn't go all the way to zero because once you're one-dimensional, you have no proper vibration. So one-dimensional type, strong minimal type, would have no proper vibration. So you stop at some point, at some non-algebraic point. So with Q non-algebraic. It's possible that everything I've written down, the original P should be non-algebraic. Zeros. I suppose they trivialize it to start with. Okay, so you have some image which has no proper vibrations, and you let G be the binding group of Q. You have an image which has no proper vibrations. It's also C-eternal because it's the image of C-eternal, right? It's also weakly C-orthogonal because P was weakly C-orthogonal. So yeah, we can say that here. So P C-eternal. I can assume P is weakly orthogonal because I'm trying to prove P squared is not weakly orthogonal. Assume that P is weakly orthogonal. Theorem is fine. Particularly Morley applies. If Morley tells me, Morley implies that G is either equal to its linear part or Abelian part. But now the fact told me that in the linear part it's commutative, and the Abelian part is Abelian varieties, so it's commutative regardless. Sorry. So the Morley tells me that if I have a binding group, if I have types, so here I'm looking at Q, which is weakly orthogonal and C internal, then its binding group either agrees with its Abelian part, so it's an Abelian variety of constants, or it agrees with its linear part, so it's a linear algebraic group. If it's a linear algebraic group of the constants, then it's commutative. And if it's a Abelian variety, that's also commutative. So in either case, G is commutative. And this means that I have this homogeneous space, but the group is commutative, so it's a principal homogeneous space. G acting on this is therefore principal. Namely, the action is determined, the action of some element of the group is determined by its action on a single point. And so if I take 2 points, if A and B realize Q. I apply the Morley and the facts Q. They realize Q, then then B has to be in the definable closure of B together with A together with the constants. Because if I have an automorphism fixating A and constants, it's in the binding group, but it's trivial on A, but it's determined by its action on A, so it's also trivial on B. Which tells me that B, now if I guess A could have equal B here, so I want to take. So if I choose independent realizations, then I'm getting that B must fork with C over BA. It's not algebraic over A because they're independent realizations, but it becomes definable when you add constants. So this must fork, and so that implies that the tuple A comma B must fork. That's realization P2. So it's not weakly orthogonal, there's some forking with the constants, but they're based around. Am I actually done, or do I have 10 minutes? 2? Okay. I'll just make some remarks. So that's how you put the 2 pieces together. Maybe I'll just make some sort of verbal remarks. First of all, as I said, this is sort of one application of this theorem 2, and we exhibit other applications. So, for example, as you might imagine, if you take a 2-dimensional type, you get a lot of information because you look at this in the direction. It's either nothing or everything, and those are easy cases to study, or it's one. And so it's a reduction to the study of one-dimensional types. So what we get is a complete classification of two-dimensional types in DCF0 with constants that are internal but not equal in terms of the actual equations. Classification. And there are some other, but these also have sort of geometric articulations. So that's one comment. The other comment is about CCM. I mean, many people, it's not very well known theory. I'll just say some words about inferior complex manifolds. I said that this also goes through. The first part goes through because of the generality of the setting, which I guess is written here. So CCM is also totally transcendental, and there is a zero definable algebraic closed field, namely the complex field on the projected line. It's pure. And so the first part goes through, but what about this fact, right? Is it true that if you take an autonomous type, then that's internal, then its binding group, if it's linear, has to be commutative? And actually, it's a question that Sergey asked me when I was speaking about a different project where we also used this fact in a different paper at Fields on the 170th. I didn't know the answer, and Remi was in the Zoom audience, and we started talking about whether it was true in CCM, and we found that a theorem of Fujiki's on relative Abelian reductions could be used to prove something even stronger. So in CCM, the failure is even greater. There are no such. So no linear algebraic group arises as a binding group in an autonomous type. So there's no such. Using this Abelian reduction thing, so there you can figure out its answer. But then that Abelian albinism, Fujiki's relative albinism made us think about what about something like this in an abstract setting that grows. So the whole project actually started with this question. And I'll stop there.